One type of pericyclic reaction that is very useful is the cycloadditions, in particularly the study of Diels Alder reactions, which are 4 plus 2 cycloadditions, and that's the number of electrons involved. Example of that is, say, we have butadiene, and this is 1, 3, 1, 2, 3, and 4 butadiene. But what we see here is what we call the S-cis conformation, which is not the most stable. The most stable conformation, I'm going to draw it here, is the strand. So this is again 1, 2, 3, and 4, 1, 3 butadiene. And we have this in the other conformation here. So S-strands, conformation, and S-cis. But all of these reactions happen through, they occur through cyclic transition states. And if we have butadiene in this conformation, that is the reactive conformation. And so butadiene plus ethylene, we're going to do this. In moving electrons in a cyclic fashion, the product of the reaction is going to have, I'm using 6 electrons in that movement. And we're going to make here a double bond. And what's interesting here, and we have discussed it in a previous video, is that we have here a couple of new sigma bonds, which are stronger than pi bonds. So that makes the reaction in terms of enthalpy, say exothermic, but the reaction still involves a decrease in entropy because we're adding 2 molecules and forming 1. So always addition reactions involve a decrease in entropy. But since we are making 2 new sigma bonds, as an expense of the difference here is 2 less pi bonds, let's say. So there's more energy release. So the reaction is then exothermic. So the reaction is exothermic, meaning energy is released. And so when you do your change in Gibbs-free energy, is that? So even though this term is unfavorable, we will have minus and minus here, that's plus. But we want this term to be larger than that. So typically we work these reactions, and in general, addition reactions are favored at low temperatures. We have discussed that before. So the cycloaddition at low temperature, but if we wanted the opposite reaction, say the retro Diels Alder, in which you will be breaking this bond. That is the other arrows show here the retro, so the opposite reaction here. You will use higher temperature. In other words, if you want to get the addition, you work low temperatures. Otherwise, if temperature is too high, then you will have the retro Diels Alder. There's a few things are important then regarding the Diels Alder reaction. One is then again that your reactive conformation is the strands, and that makes some dienes not reactive. For example, if you had a diene such as this, notice that this diene is locked in this conformation, and we cannot get it. This, notice, is similar to that, so in conformation, and we cannot get it in that conformation that we needed to do the pericyclic reaction. So this will not react if we put it with, say, a dienophile, so no reaction. But, however, there are other dienes that are fairly much more reactive. And these are the ones that have, say, locked conformation in such a way that you have the 2 double bonds to the same side. That's the case of cyclopentadiene, for example. Here, you notice this part is locked, so very reactive. Or you can have furan, for example, as well. So these are also dienes, and they are very reactive because they're locked into that conformation. This will be non-reactive. So that's one thing to take into account in the Diels Alder. There are other considerations such as stereo specificity. So let's say that I start, and now I'm going to now add substituents to this, to the diene. Now we know this is in the S-cis conformation, but we can have the substituent, say, at the dienophile. Let's say that I start with these alkene, and I will have added 2 metal groups. Notice that these are pointing to the same side, so it is cis. So when the cycloaddition occurs, that reaction is stereo specific, meaning then that the product will have these 2 to the same side. And again, what's important then is this is kept. If this was trans, there will be opposite side. Now this compound, notice that we have a change in hybridization here from sp2 to sp3. And now by the 2, same here, the 2 metals are now pointing to the same side. If you have those 2 industries, that will be the same. I mean, this compound is a meso compound. So the enantiomer with the 2 in, say, industries will be the same. So stereo specificity is important in Diels Alder, and we want to continue doing that with problems.